Okay, so this problem is an ideal transformer problem, and it's asking to find the power delivered to, which is the same as the complex power absorbed by, the 10 ohm resistor. So this 10 ohm at the top between A and B terminals, and then 10 ohm at the bottom between C and D terminals. Okay, so if we're going to do this, to me this problem is pretty simple at first because I can combine these two resistors in the top in parallel and also in the bottom in parallel. So I would have in both cases 50 in parallel with 10, and so that's going to be 50 times 10 over 50 plus 10. So that's 50 times 10 is 500 over 60, and so that's 56, and so when we use that value, we get 8.33 ohms. And so in both cases we have 8.33 ohms. Now we know that we can take the formula Zn equals Zl over A squared to move the impedance that's on the output side of a transformer to the input side of the transformer. So our A here is 1 to 4 on this side and 1 to 3 on this side. So when we calculate the input impedance on one side, even though the resistances look the same on the secondary sides of both of those transformers, on the primary side it's going to look like we have a current source of 1 angle 0, and that's in RMS. And then over here we're going to have so A is 1 to 4, so A is, we normally write it as A to 1, so this would be ZL well, in this case ZL is 8.33 ohms over A squared. Well, A is 1 divided by 4, so 0.25 squared, so 0.25 there. So this is 133.3 ohms on the top side, and on the bottom side we have also 8.333 over, but this time it is 1 to 3, so that's 1/3 squared. And so when I do that, I get 75 ohms. So okay, so the reason I would like to know this is because I really would like to know the voltage, and I'm going to find the voltage with respect to the dots because that is important. I've always said I would like to know my voltages with respect to the dots because then I can use the standard formulas and not have to worry about positive or negative signs. So if I do that with the dots, you'll see the location right there, and so on the 133.3 ohm, I get 133.3 times the current, which is 1 angle 0. So this is going to be angle 0 volts, and I'll call this V1, and this one down here at the bottom I'll call V2. So V1 I have is 133 angle 0. V2 I'm going to have, I want that current I is also flowing this way through that, so I'll have 75 angle 0 for that, for my voltage. And so, okay, now if I look at V1 side, then if I call this voltage up here V3 and this voltage here down here call it V4, notice that I can easily do what I said, and that is use the standard formula with a plus, and that's going to be, okay, the formula should be V3 and this one would be V1, so V3 over V1, V3 over V1 equals 1 over 4. And my other equation is V4 over V2 is equal to 1 to 3. And that's because I've used that proper form for the dot convention being with the plus sign. And so this tells me that V3 is equal to 133.3333, and I divide that by 4. So I get 33.3333, and V4 is going to be equal to V2 over 3, so 25. And so, okay, these are in RMS values, so I know I should be able to take S equals VI conjugate. Don't need the 1/2 in the front because they are RMS. And for us, this is going to be super simple because these are all resistors. So this is going to be V over R conjugate. Well, VV conjugate, that's magnitude of V squared divided by R. Okay, so for us, we're going to have, for the 10 ohm at the top, and the reason I've done it with voltages is, notice these two resistors, the 50 and the 10 ohm, in both the top and the bottom are in parallel, so they have the same voltage across the 10 ohm resistor. And so I'm going to say S10 top is equal to magnitude of V3 squared over 10. So that is going to be 111.11 watts, and S10 bottom is going to be equal to magnitude of V4 squared over 10. So that's going to be 62.5 watts. They're both purely real here, which is not surprising. And let's see if it checks out with what we had. Yes, it does, so we're in good shape. Now, there was another problem in the next homework where it talked about doing the same setup, but rather than doing it this way, let's see if I can just copy it below. I'll just add a new page and put it over here. Okay, so the only difference between the two problems was it said what's going to happen and calculate the power in the same case when I connect. When you think of connecting A and C and B and D. Well, now notice this doesn't, you can't just take the 10 in the parallel with the 50 on one side and the 10 in the parallel for the 50 on the other side and backtrack, because if you do, what's going to happen? Well, what's going to happen is all of a sudden you're going to have a problem with what is the actual load impedance, because you have these transformers that are sort of connected up, and what can you say about those impedances? So it's not quite as obvious what would go on right there. Okay, so let's see if we can work the problem this way. Well, one thing we should realize first is about the ideal transformers. Remember, the ideal transformers are expecting the voltages. If we use the standard equations, we should call this, like we did before, we should have V1, this can be V2, this should be I think I called it V4, excuse me, V4, and this one can be V3. Okay, so we label them all with the dots. Now the other ideal transformer setup is the current should come into the dot, so this way should be I1, into the dot, this way should be I2, for the input side of the transformers, and it should come out of the dot for the output side of the transformer. So here's I3, and here is I4. Okay, so now notice that when I do this, one thing I can say is, obviously, if A is connected to C and B is connected to D, I can see that clearly the 50 and 10 ohm at the top are in parallel, the 50 and 10 ohm at the bottom are in parallel, just like before, but now all of those are in parallel because terminals A and C are the same and terminals B and D are the same. So we have 50 in parallel with 50, and that is obviously in parallel with the maybe I should write it a different way like I did before. We have 50 in parallel with 10, which is also in parallel with the 50, in parallel with 10 from the other side. And so before, when we calculated that, so we had 50 and 10 in parallel, which we said was 8.333 ohms, and both of those are in parallel, so, and that's the same on both of them, so that should just be divided by 2, so this is 4.167 ohms. And so basically I have I can think of having the transformer and if I think of the bottom one drawn up there above it, actually, since it would be sort of tied back around, you can think of sort of like a gerbil loop or whatever. So here's the dot on this one. I would have the dot up there. That was not a very good transformer at all. Let's draw it again. So I'd have the dot up there for that one. So here is V3. Here is V4. Now notice one thing we can say is V3 is equal to minus V4, because they're in parallel with each other, and that's an important equation for us. Okay, so one thing that's going to happen is the power in both of these 10 ohms, since everything is tied in parallel, well, okay, that just tells us straight away what? It tells us the power in the 10 ohm at the top is the same as the power in the 10 ohm at the bottom, because they have the same voltage across them. Okay, so we just need to find out what that is. So if we find V3 or V4, then we're in good shape. We also know that, what did we have? We called this I3 coming out of the dot here and I4 coming out of the dot there. And this was our 4.167 ohms. And so, okay, the next thing we can take is we have that 1 amp current source, and we know that I1 and I2 are both 1 angle 0. Well, straight away that tells us what I3 and I4 are, right? Same thing we did over here. If we know I1, we can use the equation, the ideal transformer equation. I3 over I1 is equal to, it's the easy way to remember it for me is like V3 over V1 is equal to N2 over N1, and I3 over I1 is equal to N1 over N2, the opposite of that, so that will be 4 to 1. And we can also say I4 is equal to what is it? Well, maybe I should say I4 over I2 is equal to N1 over N2 for that one, which would be N4 over N2, maybe I should say. I should have said N3 over N1 for the the other one, but it should be this one divided by that one. So 3 over 1. Okay, so this tells us I3 is equal to 4I1, and this tells us I4 is equal to 3I2. Well, I1 and I2 are both 1 angle 0, so this is going to give us 4 angle 0, and this is going to give us 3 angle 0. Alright, so our next calculation is trying to find V4 and or V3. We do indeed know they're the same, right? Because they're in parallel. And what are they? Well, I have this equation right here. Notice if I4 is going that way, down on the right side it's going, oops, excuse me, drew that poorly. It's going up on the left side. So that gives me the ability to write this question, this current in the middle branch. I can write that I, well, maybe I should be careful and say minus I3, right? That's the current going into it of the top. I mean, from this node right there, it's going into it. From the one transformer, plus I plus I4, sum up those currents, they'll be equal to 0. And so that gives me I in that branch is equal to I3 minus I4, and so that's equal to 4 angle 0 minus 3 angle 0, so that's 1 angle 0. Okay, then the voltage V, so that I have it this way, I can just take this voltage as that I times 4.167. So, and if I just want to call that, I'll make sure it's clear, that's the same obviously as V3, but V is equal to this I times 4.167. So, since I was 1 angle 0, this is going to make this 4.167 angle 0. And I can take magnitude of V squared over... Oh, wait, excuse me, that's the voltage. I don't actually want to know the power in that 4.167 ohm resistor, but I do need to know that voltage, because I want to know again what it is in the 10 ohm. The 10 ohm is going to have that same voltage across it because they're all in parallel, so V10 ohm, either one, is going to be 4.167. That's the voltage squared. Oh wait, no, that's the voltage right there, excuse me, volts. So power in the 10 ohm is going to be magnitude of that voltage squared, 10 ohm over 10. So if I take 4.167, and I square it, and I divide it by 10, I get 1.736 watts. So it's obviously a good bit different if we indeed do that scenario. So that, and again, it's the same for the top or the bottom because the same voltage is across both of them. Okay, so that sums up this particular two-set problem with this transformer.